My name is Carlos Rodriguez Delgado, and this is my C++ final. This is part 1. I would submit 3 20-minute videos because at first I did a 1-hour video and it was hard to submit. Um, in this video, I would be talking about multi-threading and concurrency in C++. I'm going to try to keep the explanation simple and beginner friendly so that I won't get confused or anything like that. I feel like the main idea is that sometimes a program needs to do more than one thing at the same time, or at least make progress on more than one task during the same period of time. An example that I can think of right now is that when our phones can play music while we're scrolling through an app, when a web browser can load one website while another tab is already open, when a video game can play sound, check the keyboard input, and update the screen all at the same time. I feel like these are all examples of a program handling multiple tasks at once. In programming, we call this idea concurrency. Concurrency means that multiple tasks are making progress during the same time period. One way to create concurrency is by using threads. A thread is like a separate path of execution inside a program. So I feel like instead of only having one path running from top to bottom, we can have multiple paths running. And today I'm going to show you a simple C++ program that uses threads, and I'll try explaining the code step by step, and then I'll run the program and explain the output. First, let's take a look at the top of the program. We have 3 include statements. The first one is include IOStream, which this allows us to use cout, which lets us print information to the screen. The second one is include thread, which this one's very important for this program because it allows us to create and use threads in C++. And then without the library thread and task number 1, without the library, we would not be able to write the code like this, for example, where it says thread t1 in parentheses task 1. And then the third one is mutex, which this gives us access to something called a mutex. A mutex is used to protect shared data when multiple threads are using the same variable. I'll explain more about that later, but for now, we just need to remember that IOStream is for output, thread is for creating threads, and mutex is for protecting the shared data. Then, of course, we have using namespace std. This lets us write cout, thread, and mutex without writing std in front of them every time. Then we also have our global variables, in which we have 2. The first one would be the int counter, which creates an integer variable called counter, and it starts at 0. This variable will be shared between multiple threads later in the program. The second one is over here called mutex mtx. This creates a mutex called mtx. The mutex is going to act like a lock, which means that only one thread should be allowed to change the counter at a time. This is important because if 2 threads try to change the same variable at the same time, the program can give the wrong result. So the mutex helps prevent that problem. Right over here in task number 1, we have our first function. The function is called task1. It is a simple function that counts from 1 to 5. Inside the function, we have a for loop that starts with I equal to 1, and it keeps going as long as I is less than or equal to 5. Each time that the loop runs, I increases by 1. Inside of the loop, we print task 1 colon, and then we print the value of I. So this function would print something like task 1 colon 1, task 1 colon 2, task 1 colon 3, task 1 colon 4, task 1 colon 5. This function is not complicated by itself. but the important part is that later we will run this function using a thread. Now we have another function right over here called task2. This function is almost as the same as task1 because it also counts from 1 to 5, and the only difference, of course, is that it prints task2 colon instead of task1. So this function will print task1 colon 1, task2 colon 2, task2 colon 3, task2 colon 4, task2 colon 5, which these two functions are simple on purpose because right now my goal is not to make any of the functions complicated, but the goal is, I feel like, to understand how threads allow both functions to run concurrently. And then over here we have our int main, which means that we're already inside of the main function. The main function is where the program starts running. The first we do is print a title, which makes the output easier, which just makes the output easier to understand, which is this is our title, multi-threading example. It shows that the first part of the program is about multi-threading. And then we can go right over here to one of the most important parts of the program where we create the through threads. The first line, it's gonna be thread T1 parentheses task 1, which this creates a thread called T1, and that thread starts running the function task 1. The second line over here would be thread T2 and in parentheses task 2, which creates another thread called T2. That thread starts running the function task2. So instead of calling the functions normally like this, like for example, task1 and then parentheses, open parentheses, task2, open parentheses, close parentheses, we are running them as separate threads, which means that task 1 and task 2 can make progress during the same time period. This is concurrency. The program is no longer just doing one thing at a time in a simple like top to bottom order, but instead there are multiple threads working, which means that the operating system decides when each thread gets time to run. Because of that, the output can look mixed. Sometimes task 1 might print first, and then sometimes task 2 might print first. The exact order is not always guaranteed, but this is normal when working with threads. Something that we should notice is, for example, right here in line 55, where I have T1 dot join parentheses, which means that after creating the threads, we have these two lines, which means that the word join in this case means wait. So we can write T1 dot join. We're telling the main program to wait until thread T1 finishes, and then write T2 dot join. In this case over here, we're telling the main program to wait until thread T2 finishes. This is important because we do not want the main function to end before the threads are done. If the main program ended too early, the threads might not finish their work. So join makes the threads finish before the program continues. Now, in this part of the video, I'm going to run the program so we can see the output. When I run it, let me just run it first. Right now that I'm running it, notice how the output from task 1 and task 2 might be mixed together, which this happens because both threads are running during the same time period. And right here, we can see the input, task 1 and task 2 both printed their numbers. Their order might not always be exactly the same every time I run the program. That is because the operating system controls the scheduling of threads, and this is just a simple example of concurrency. Both tasks are making progress during the same period. Now let's move on to the other function that I have over here. This function is its purpose. It's mostly to demonstrate the shared data, which is this one right here, void increase. And then this is the entire function. I consider this the second part of the program. The purpose of this function is to increase the counter variable. The loop runs 1,000 times. Each time the loop runs, the counter increases by 1. So if one thread runs this function, the counter should increase by 1,000. But later we are going to use 2 threads. If 2 threads both run this function, then we expect the final counter value to be 2,000. One thread adds 1,000, the other thread adds 1,000, so 1,000 plus 1,000 equals 2,000. But there is a problem. The variable counter is shared, which means that both threads are using the same variable. When multiple threads change the same variable at the same time, something called a race condition can happen. A race condition is for when the result depends on the timing of the threads. Which this means, in other words, that if 2 threads try to change the same data at the same time, the program might not work correctly. That is why we use mutex. Over here in mutex, this locks the mutex, which means that when a thread reaches this line, it tries to lock the mutex. If no other thread has locked it, it means that then this thread is allowed to continue. But if another thread is already, but this means that like if another thread already has the mutex locked, then this thread has to wait. Which this ensures that only one thread can enter this protected section at a time. And then right here in our counter, this means that this line increases the counter by 1. This is the important shared data that we are protecting because since both threads are trying to change the counter, we do not want them changing it at the exact same time. So we put this line between lock and unlock. Over here, this line, it's for the mutex to unlock, which means that after the counter has been increased, we unlock the mutex. Which this allows another thread to use your protected section. So this process is lock the mutex, change the counter, unlock the mutex. This keeps the counter safe and it prevents that race condition that we were talking about early on. And then over here, where we have cout and we want to go back to the main function where we print another title over here, which is shared data example. This separates the first example from the second example because the first example showed basic multi-threading, and then the second example is going to show us what can happen when threads share data. And then right here, T3 and T4. Right here, we're creating 2 more threads, which the first one is called T3. It runs the increase function. The second thread is called T4, and it also runs the increase function. Now we have 2 threads both increasing the same counter variable in which each thread runs the function 1,000 times. That means that the final counter value should be 2,000. But because we use mutex, the counter is protected. The threads cannot change the counter at the exact same time. They have to take turns. And then over here, we use join again for T3 and T4. which this tells the main program to wait for both threads to finish. The main program waits for T3, then it waits for T4. After both threads finish, then the programs continues. And then over here, we have our final output, which in the end we print the counter value when, since both threads increase the counter 1,000 times, the final value should be 2,000. And then because we use the mutex, the result should be consistent, which this brings us to the meaning that the program should reliably print final counter value that equals to 2,000, which shows that the mutex protected the shared variable. Now we will run the program again. First, I want to say that we should see the multi-threading example, then we should see the shared data example, and then at the end we should see the final counter value. And let's run it one more time. See if you can see right here. Here's the output where we can see task 1 and task 2 messages. The order might be mixed again, like I mentioned earlier, because they are running concurrently. Then at the bottom, we can see that we have the final counter value for 2,000, which shows us that the 2 threads completed their work and the counter was updated correctly. Let's go back over here to give a quick summary about everything I learned and what I went over in this video was that a thread is a separate path of execution inside a program. Multi-threading means using multiple threads in the same program. And I also know that concurrency means multiple tasks that are making progress, of course, during the same time period. And in this program, again, we use threads to run task 1 and task 2, which showed us how 2 tasks can run concurrently. Then we use 2 more threads to increase the shared counter. Since we used both threads, they were both using the same variable, we had to be careful, which is one of the reasons why we had to use a mutex. And just to remember, a mutex acts like a lock and makes sure that only one thread and only one can access the shared variable at a time. Without a mutex, we could get a race condition, which means that a race condition happens when multiple threads try to access or change shared data at the same time, which in the end, the final result becomes completely unpredictable. So, going back to the main ideas from this program at the start with that, where that threads allow different parts of a program to run concurrently, and then shared data can cause problems. Mutex helps. A mutex helps to protect the shared data, and I feel like this is very important to talk about because in many real world programs use concurrency. For example, some of those could be in games, web browsers, apps, and operating systems all use these ideas. Any kind of operating systems for computers, phones, tablets, everything all like that. We also saw that multi-threading can make programs faster and way more responsive. But of course, like programmers have to be careful when these threads share data. And that is it for this for part 1 of my final, which was explaining just the basic idea of multi-threading and concurrency in C++. Thank you for watching, Mr. Powers.